they have future?
So we're going to be looking at inverse trig functions.
So after AP exam, can we have a future, please?
Possibly, if you can find a suitable field.
That house, my house. Sleep all day. Future.
So our first step is going to be to review trig function graphs, and then we're going to review our material for the inverse function theorem.
I'm not sure about.
And then from that, we're going to develop graphs of the inverse trig functions and their derivatives. And if we have time, we're going to develop some other relations between them, but probably tomorrow we're going to develop relations between the various inverse trig functions. ITF's inverse trig functions. So that's our plan for the next 2 days. And so Justin, if you are following along at home, the direction that I gave to my students here was to sketch all 6 trig functions and they're working on that. So I'm going to pause the video to give them time to finish, and you can pause too and sketch all 6 trig function graphs. Okay, here we go. I'm going to claim that you can successfully sketch all 6 trig function graphs knowing only 2 pieces of information. Number 1, the zeros of sine and cosine, and number 2, the quadrants in which the functions occur. So if we go to, let's call this pi, let's call this 2 pi, like so. Let's call this pi, let's call this 2 pi, like so. And so the graph of sine is going to up, down. I did the same thing Danielle did. It was quite symmetric. Elliot can come along and critique my graph. Yep. And so there is the graph of sine. And here comes the graph of cosine. So, and I do my best to draw it. Well, I don't know if it's my best, but I attempt to draw it so that we have origin symmetry for sine. In other words, sine is odd, and we have y-axis symmetry for cosine because cosine is equal. Okay, and there are our graphs. Notice that the zeros for sine are going to be at the integer multiples of pi. So sine x equals 0 implies that x equals k pi, and cosine x equals 0 is going to occur at the odd multiples of 2 pi. In other words, x equals 2k plus 1 times pi over 2. The odd multiples of pi over 2. Did I say 2 pi? And then pi over 2. Everybody good with that? And then finally, I just want to observe that as we march across from 0 to 2 pi, what we're doing is marching across quadrants on the unit circle. So from 0 to pi over 2 is quadrant 1. From pi over 2 to pi is quadrant 2. From pi to 3 pi over 2 is quadrant 3. And from 3 pi over 2 to 2 pi is quadrant 4. So that sine is going to be positive in quadrant 1 and 2, negative in quadrants 3 and 4. Cosine will be positive in quadrants 1 and 4, and negative in quadrants 2 and 3. This is all the information that we need to construct the graphs of tangent, cotangent, secant, and cosecant. And here's how. If I write tan x equals sine x over cosine x, then I observe that it will have zeros where sine is 0, and it will have asymptotes where cosine is 0. In other words, where x is equal to k pi, we have a 0. And where VA's vertical asymptotes where cosine x is equal to 0, or in other words, x equals 2k plus 1. And so this allows me now to graph by dropping a vertical asymptote at pi over 2, and another one at 3 pi over 2, and if I need, another one at negative pi over 2, etc. And then I can mark my zeros exactly in between at 0 and pi and negative pi. And now I'm going to use the quadrant information to tell me the behavior near the asymptotes. In quadrant 1, both sine and cosine are positive, so my graph must go up to positive infinity. In quadrant 2, sine is positive but cosine is negative, so my graph must come up from negative infinity. Whoa, wrong. Must come up from negative infinity and hit 0. And then in quadrant 3, both sine and cosine are negative, so that tangent will be positive. And so my graph must look like this. See? Easy logic. What about cotangent x? Same story, but upside down. Here, I'm going to have zeros where cosine is 0. In other words, where x is 2k plus 1 pi over 2. And I'm going to have vertical asymptotes where sine x is equal to 0. In other words, where x is equal to k pi. And so that's going to give me vertical asymptotes at 0, pi, 2 pi, negative pi, and negative 2 pi. And I'm going to have zeros at x equals pi over 2, 3 pi over 2, negative pi over 2, etc. And now I use the quadrant information. In the first quadrant, sine and cosine are both positive, so my graph must come from positive infinity. In the second quadrant, sine positive, cosine negative, so the graph must go down to negative infinity. In the third quadrant, sine and cosine both negative, so the graph must come down from positive infinity. In the fourth quadrant, cosine positive but sine negative, so the graph must go down to negative infinity, etc. Does everybody see the logic here and how in just a couple of seconds I can accurately generate a sketch? You taught me through the graph of secant then.
It's 1 over cosine.
Okay.
We look at the graph of cosine.
Well, okay, so we know the graph. Actually, all we need to know are the zeros and the quadrants, right?
Wait, do we really not going to look at it? I think we need 4. Wait. We need 4.
We need 4 whites.
Quadrant.
Yeah, we're going to do that.
And is it going to be like graph of x prime?
You don't need to work nearly that hard. You simply need to identify zeros and vertical asymptotes for secant, and you're good to go.
Is the pi over cosine is the 0. So is the
Ah, yes.
And
But is that the only asymptote?
no, 10k every how do we call this? Pi over k whenever k is.
Not pi over k. Okay, so what happened back here, I'm going to fuss at you a little bit. What happened back here is that I was demonstrating some things that you didn't understand, and you didn't stop me. Oh, we need to come back over here. Pay close attention to the zeros of sine and cosine, and why they work. What is this saying? X is an integer multiple of pi. Yes. And x is an odd multiple of pi over 2. Now, come back to secant. Let's identify zeros and vertical asymptotes.
Vertical asymptote is 2k plus k and
2k plus 1 times what?
pi.
You.
Pi over 2k.
Yes. Pi over 2. We're looking at odd multiples of pi over 2. And if you're confused about that, take a look at your unit circle. Alright, so those are the vertical asymptotes. What about the zeros? Yeah. There are no zeros. Because the numerator is never 0. Yeah. Alright. So that is enough. We can put in our vertical asymptotes. And now we're ready to start thinking about quadrants.
When it goes to like pi over 2, it goes to positive infinity
From which direction? Left or right?
from
From the left. Yep, that's right. Where is the minimum value? If it doesn't hit 0, then it has to hit a minimum in here somewhere.
1.
1. Right. Since the largest value of cosine is 1, the smallest value of secant is 1. And we have the same symmetry that cosine has. Okay? What happens over here?
And this is to from right to negative infinity.
Good. What's the largest value?
Negative 1.
You got it. And then we just repeat it. Okay? And that's that. And finally, y equals cosecant x. Josh, you're on.
Vertical asymptotes first. So we're going to have them at every couple,
Got it?
which means vertical asymptotes at negative pi, 0, pi, 2 pi.
Did not mean to do that. There we go. Good. Keep going.
Let's see, there are no zeros.
Good.
So, I did some values, so like pi over 2 is 1. 3 pi over 2 is negative 1.
Good.
Negative pi over 2 is negative.
So what shape do we have?
So we have, starting there, we have concave up here,
Yep.
and concave down here,
Yep.
and concave down here.
Yep. Notice the origin symmetry of cosecant. Yep. Exactly. Now all of this was not complicated. We had to think it through a couple of times. We want that thinking through process to be automatic. So sitting more than some other class, you can sketch for yourself the graphs of the 6 trig functions so that it's automatic. Now why do I want these graphs? I want these graphs because over the weekend we had a theorem. And our theorem was the inverse function theorem. So let's take a minute to review the inverse function theorem. there's a condition. If f prime of x is positive on the interval a to b, or if it is negative on the interval a to b. In other words, it has the same sign on the entire interval. Then, two things. F inverse exists on a to b, and f inverse prime is 1 over f prime of f inverse on that interval. Now the reason for the first part, the existence part, is fairly straightforward. Here is a function whose derivative is always positive, and you can observe that the fact the derivative is positive forces the function to be increasing, which forces it to be one-to-one. And one-to-one functions have inverses. Likewise, if f prime is always negative, well, I came perilously close to 0 there, then it will be always decreasing, and therefore always one-to-one, and therefore has an inverse again. And the reason that f inverse prime is 1 over f prime of f inverse is simply this. If y is equal to f inverse of x, then f of y is equal to f of f inverse of x, which is equal to x, because the function and its inverse cancel each other. And therefore, if I take the derivative, f prime of y times dy dx, taking the derivative with respect to x, and I take the derivative with respect to x on the other side, then I get the fact that dy dx equals 1 over f prime of y, and y is f inverse of x. Just like so. Now, practically speaking, sometimes we are going to use the inverse function theorem directly in this form, and sometimes it's more convenient to walk through the two-step logic process that we did here to get there. And that's what we're going to do actually with our inverse trig functions. Sure can. Okay? So, what this means is that if I want an inverse sign, I need to first find a domain for which the derivative of sine is always positive or always negative. Does that make sense? So coming back to here, like so, if I look at y equals sine x, I can see that from from negative pi over 2 to positive pi over 2, sine x is increasing. And right at the end points, we will be, even though the derivative is 0 at the end points, we will be able to include those endpoints with the understanding that f inverse prime at those points will be infinite. Okay? So this means that I can take the function f of x equals sine of x on the interval negative pi over 2 to positive pi over 2. And I'm going to call it capital S sine of x. And this is going to be our invertible function. F inverse of x is going to be inverse sine of x. Now, I didn't have to choose that domain. I could have chosen any domain for which the derivative has a single sign, possibly within points. Okay? Okay? So, if I do that, then we can sketch the graph by reflecting the graph of sine x about the line y equals x. And the way I usually do that is with what I call a 3-point solution. I know 3 points on the graph of inverse sine. I know that when x is equal to 1, inverse sine of 1 will be pi over 2. Because sine of pi over 2 is 1. And I know that the inverse sine of 0 will certainly be 0. And I know that the inverse sine of negative pi will certainly be negative pi over 2. And so there's our 3-point solution. Furthermore, from the inverse function theorem, I know that f inverse prime is 1 over f prime of f inverse. So this indicates to me that for any y value for which f prime is positive, the corresponding x value will have a positive slope also. So since f prime is positive on the entire domain of sine here, f inverse prime must be positive as well. This function must always be increasing. And we'll work out the concavity relationship later. But here's going to be our graph of inverse sine, just like so. And to keep our head straight on that graph, I recommend a 3-point solution. What about the derivative of inverse sine? I would like to solve this problem. And there's a couple of ways that we could do this. We could appeal directly to the inverse function theorem. Tomorrow we'll actually come back and do that. Today what I'd like to do is to do it in a more natural manner by taking the sine of both sides. If y is inverse sine of x, that automatically means that x is the sine of y.
That's what you're doing.
No? Oh, this is the inverse, the graph of the inverse of sine. Right? And this is the relationship that obtains between the variables. Now if I take the derivative with respect to x on both sides, right, easy side first, that's 1. And what is the derivative over here?
Okay, y, and then dy dx, and
Cosine 1. Yep, that's exactly it. And so therefore, I get this relationship, dy dx is equal to 1 over cosine 1. Isn't that nice? And you see the inverse function theorem staring at you, right? dy dx is 1 over f prime of f inverse of x.
we learned this last year, right?
Yeah.
Do it.
Yes.
Well, some
It
of us
was
did.
on the 8th test.
Yeah. But now, the only trick about this is that this is implicitly defined. And in terms of style, this is not so good because originally we were given an explicit y equals inverse sine of x. So we would like to be able to express this in terms of the variable x. And it occurs to me that the cosine of y is related to the sine of y through the Pythagorean theorem. Specifically, cosine squared y plus sine squared y is always 1. And that means that the cosine of y is root 1 minus sine squared y, and sine y is x. So that when the dust settles, I have a very lovely relationship for the derivative of the inverse sine, which is 1 over root 1 minus x squared. Now the fascinating question is that we crossed over into a different family of functions, right? Here we were working with inverse trig functions, and all of a sudden, boom, I have an algebraic derivative. So that suggests a very deep mathematical relationship. I will not cover it this time. Okay. How are we doing? Does this make sense so far? Yes, ma'am. Because sine y is x. That's the beauty. The beauty is part of this. That's the key move in some ways. So the key move is really taking the sine of both sides. Let's do the same thing for inverse cosine. I figure we'll be able to accomplish at least inverse cosine and inverse tangent before the day is up. Okay, so first of all, a graph. And our graph can come from a 3-point solution. What 3 points on the graph of cosine do you know that we can invert?
Excuse me. 1, 0.
Good. Right, it's 0, 1, so the inverse cosine of 1 is 0. That's right. We go over to this point right here, and we get 1, 0. Good. What other points do you know?
Half times 0. So then it's called 0 half.
Yeah. Good. So there's our second point.
-1.
But it's not 0. What is the angle whose cosine is -1? It's pi. Yep.
Oh,
And that gives us our third point here. So, and now we can go just like that. And here's our graph. Ta-da. Notice that at the end points, right here and right here, dy dx is equal to infinity because we have vertical tangents here, because we have horizontal tangents on the graph of cosine at the corresponding x points. Does that graph make sense to everybody? Good. Yes, ma'am. Yeah. How do you know about the direction concavity? First of all, does it make sense that we have an always decreasing graph right here? Because essentially what I did was to find a piece of the graph of cosine where the derivative had all the same sign. Okay? And so then the next question is the question of concavity. And we haven't really addressed concavity. We could. But yeah, with a second d-test, right? We need some information. But I just appealed to a different ideal, which is that since the graph of cosine has horizontal tangents at 0 and pi, therefore the graph of its inverse must have vertical tangents. And so I drew the graph from here coming vertically up and going up vertically up that way. And that forced the direction of the curve, if that makes sense. To go the other way, I would have had to come out horizontally. And that isn't. Does that help? Good. Now what about the derivative? So our task is y is equal to inverse cosine of x. Find dy dx. Guide me through. Elliot, you're on.
Like, so the derivative of when x equal 1 and -1 is infinity.
The derivative of x would be 1.
No, I mean
Okay,
cosine negative, like the derivative of y equal, like dy dx equal derivative of cosine negative 1x.
okay. We seem stalled out. We need a key move that's going to help us. Ah,
Oh, like time cosine at both sides.
okay, it's not times. It's not multiplication. It's the evaluation of the function. So we say it like this. Take the cosine of both sides. Okay. And when I do, what do I get on the left side?
Cosine x
Use
y
cosine equals.
x.
Yes, you do, because the cosine of the inverse cosine of x is x.
Yeah.
So the key move is to invert by means of the cosine. Now, keep on going. Smooth sailing from here.
So the negative sine 1 equal to 1.
How'd you get that?
Wait.
Let's see that operation. Give me your operator.
Derivative on both sides.
With respect to what variable?
X.
Ah! And this is where students will sometimes be sloppy. They will think take a derivative, but they will not think take a derivative with respect to x. No fair taking a derivative with respect to different variables on different sides. Ah. All right, now give me the derivative with respect to x of cosine y.
Negative sine like 1 over sine. Negative sine y times dy dx.
Right there. That's much better. Now what is dy dx equal to?
1 over negative.
Good. All right. Now what is the key move that's going to put this in terms of x?
Substituting both the y and the
Which gives me what?
negative 1 over square root of 1 minus cosine squared y.
Which is the same as x squared. Yep, that's exactly it. I'll go ahead and write it for the sake of your notes. And Justin. Hi, Justin. We haven't forgotten about you.
Have fun on your field trip.
Sorry, take lots of pictures. Okay. So Elliot, tell me the things you learned from this problem. A couple things.
Like first thing is take cosine. Yeah.
Of both sides, yeah.
Yeah.
You're really inverting both sides. And then what's the second thing you learned?
Like the derivative should like focus on like which like all that one is all x, so really be curious like why need add dy dx.
Struggling with the language here. How about like this? When you take a derivative, take it with respect to a specific variable. Does that work? Yep. Good. And then the rest of it is just details. Now, here's the thing I want you to observe. Just observe in passing that the derivative of inverse sine and the derivative of inverse cosine are numerically the opposites of each other, which suggests that inverse sine and inverse cosine themselves are in some sense numerically opposite each other. in some way. We'll develop that relationship tomorrow. Very quickly, let's check inverse tangent.
Let's go.
The 3 points that I recommend here are actually 2 horizontal asymptotes and a point. The inverse tangent of 0 is clearly 0 because tan 0 is 0. And the other 2 we're going to do as horizontal asymptotes because the limit as x goes to pi over 2 from the left of tan x is positive infinity. And since tangent has origin symmetry, this limit obtains as well. So that our graph of inverse tangent is going to look like this. Does that make sense? We took the graph of tangent and we inverted it about the line y equals x. We reflected it about the line y equals x. For our derivative, we're going to employ much the same strategy that Delina and Elliott used. We're going to invert both sides. And when we do, we can now take a derivative with respect to x on both sides. Yeah, you got it. So we have secant squared y dy dx. And therefore, dy dx is equal to 1 over secant squared y. And now we recognize a different Pythagorean identity. Secant squared y is the same as 1 plus tan squared y. And tangent y is equal to x. So when the dust settles, dy dx equals 1 over 1 plus x squared. Now here is where, as students, you're going to want to be smart. And the thing to be smart about is, obviously, there's a lot of information here, and you've got to find a way to take it and assimilate it and make it your own.
Right.
If you try to go through by memorizing it as new facts, it's going to fail for you. So instead, what you want to do, part of your assignment for tonight, is to derive the derivatives of the 6 inverse trig functions.
Even the cosecant.
Yep. Now, when you do, we'll nuance that a little bit tomorrow based on domain. But you should be able to. I'll just go ahead and give you ahead of time your results. The derivative of inverse cotangent should turn out to be the opposite of the derivative of inverse tangent. And the derivative of inverse secant, you should get this when you do it. We'll nuance this with an absolute value tomorrow based on domain.
Yeah, this is the
And you should get
I remember this.
this also. So just telling you ahead of time what your answer should be, you should derive those for yourselves and come up with a reasonable graph. And tomorrow we will complete this set. We'll also talk about why cotangent is the ugly stepchild. Ooh.
Ugly stuff.
Yep. And we'll extend our method a little bit to consider things like the derivative of arc sine over 2, etc.